So thanks a lot, Chris, for the kind introduction. Then welcome to my keynote about unconventional optical metrology. And since I've got a lot of interesting topics for you today, let's not waste too much time and directly dive into the details. I've got 4 different topics for you. Inverse light field illumination will be the first one. Then I'll talk about learning optimal patterns for deflectometry. The next one will be synthetic generation of material defects for training machine learning models for defect detection. And last but not least, a very unconventional topic, deep linear filtering for lensless imaging. So let's start with inverse light field illumination, and we will have a particular look at the application of transparent object inspection. Now let's consider first kind of motivation, and let's assume that our goal is to inspect such transparent objects like this big plano-convex lens here. And if we have a look on illuminating light rays here in blue that illuminate this object from the left-hand side, of course, our object will do something with those light rays and converge them to its focal point, because that is what our object is supposed to do. Now, if we consider a second instance of such an object, where we have 2 material defects present in and on our object, here in red, for example, this might be a tiny air bubble that is hidden inside our object or a larger surface defect. Then, of course, for all the parts that are still defect-free, the object will act the same way on incident light. But however, for those parts where we have the material defects, light will not propagate as before. But for the air bubble, for example, it will be scattered into multiple directions, or for larger defects, it will be redirected into some other direction than for the defect-free case. And the key intuition I want to make clear here is that both the intended shape of the object and also the material defects that we have inside them have a main influence on the propagation direction of the light and not on the intensity, as it is the cause for other kinds of inspection applications. Now, how can we use this to inspect transparent objects for material defects? The first approach would be to somehow come up with devices that allow us to sense this 4-dimensional light field. So we have 2 spatial positions on our test object, and additionally, we would need 2 further angular informations to fully characterize this spatial position and the propagation direction of the light. And another approach would be to completely shift any processing into the optical domain by using a specifically adapted light field illumination. Now, approach 1, we've done that a lot. You can read a lot of papers about that. It's a bit more difficult. You need special kind of sensors and so on. That's why we will be looking at the second approach today. Before we will look at the details how this works, I'd like to give you a quick teaser image of what you can achieve with that methodology. So here, let's assume we have this sample test object, which is a plano-convex lens. And you might be able to make out this surface defect by which this lens is affected. So apparently some part has been broken off that lens. But when observing it under this conventional bright field illumination, it's quite hard to make out the clear borders of this defect. So you would need to come up with some sophisticated image processing software to really detect the whole defective area. And now if you observe that under our specific light field illumination, you get this image here on the right-hand side as the pure camera image without doing any additional processing. So here it is crisp clear that the defective area is inside all those blue pixel area, and all the red pixels show regions of our object which are free from defects. And in this case, if you want to determine the area affected by the defect, you just basically have to count blue pixel. Every undergraduate can come up with a software that is capable of doing that. Now, how can we come up with such beautiful camera pictures? How is the concept for getting them? So first, what we need to do is acquire a reference light field for our test object. Therefore, we need one instance of our object that is completely free from any material defects. And then we illuminate it from the left-hand side with collimated rays, which all propagate parallel to the optical axis. The theoretical concept to achieve that is by placing a point light source into the focal plane of a lens. But of course, if you would like to do that in practice, you can buy off-the-shelf collimated illumination sources. And on the right-hand side, behind our test object, we need a kind of light field sensor. So for now, this is only a theoretical concept, but this kind of sensor should be able to sense both the spatial position where those light rays hit the sensor, but also the angular information. So to say the direction under which those light rays reach our light field sensor. And now to perform the inspection, the idea is to revert the direction of light propagation. And therefore, we exchange the illumination and the sensor with their corresponding counterparts in the respective other domain. So our collimated illumination then is transformed into a telecentric camera. And that perfectly makes sense because the collimated illumination before illuminated only rays that are parallel to the optical axis. And now, conversely, our telecentric camera only captures light rays that propagate parallel to the optical axis because it has its telecentric stop located in the focal plane of our lens, and all rays propagating parallel to the optical axis will be able to pass this telecentric stop. And the matching counterpart for our light field sensor is, of course, a light field generator that allows us now to emit exactly this light field that we have captured before for the defect-free object. And if we now look at those light rays propagating here, according to the Helmholtz reciprocity principle, of course, just the direction of propagation is inverted from our case before. So those filtered light rays here will be turned into light rays propagating parallel to the optical axis for parts of our object which are as before, defect-free. And those light rays will be able to pass the telecentric stop and lead to a bright image on the respective parts on our sensor. Contrary, if we have any material defects present in our object, light rays that hit those defects will be now scattered into other directions than those parallel to the optical axis. Hence, they will be blocked by the telecentric stop, and the respective part on the sensor will not get this blue light rays on the sensor. And additionally, besides just illuminating those blue rays that we have captured before, we can fill in all the other positions that are empty now, so spatial positions and angular directions with, for example, red light, and illuminate those directions with red light. And by that means, what we realize, you can kind of describe it as an okay field for the blue light rays and as a not okay field for all the other positions that we illuminate in red. And of course, the pixel of our camera that looks at this material defect, it will now, if we traverse that ray, when looking out of the perspective of the camera, so to say in the sense of a ray of sight, this ray of sight will be scattered around by our defect and now hit our sensor and get some of those red light at the corresponding point on our sensor. And this now leads us to those nice resulting images that we can obtain. Two further examples before we move on to the next topic. Here again, we have a plano-convex lens that is labeled with some text and a dot matrix barcode. And if you would like to automatically read off that information and look at it again under the conventional bright field illumination, it's quite hard to read that information. However, if we now turn on the light field illumination that is specifically adapted to this test object, you get a crispy clear image of the information you want to read off. Now, in this case, the OK field is colored in black and the not OK field in white. And a second example for a cylindrical lens that we have here, where again, we have a large surface defect affecting this test object. Under bright field illumination, you kind of can make out the defect, but it's much more easier if you turn on the specifically adapted light field illumination. Now, if you want to get a real practical view of that technique, you are more than welcome to visit us at the next control fair, where we will showcase this technique by means of a demonstrator. All right, then we can already move on to the next topic I brought to you, which is about learning optimal patterns for deflectometric surface inspection. So first of all, let's quickly recap what conventional deflectometry is about. Deflectometry is a well-established technique for inspecting objects that have a specular surface. So, for example, coated car parts or mirrors, for example. The problem with specular objects is, of course, if you observe them just by using a conventional camera, everything that you will see are the reflections of your surrounding environments in your specular surface. And deflectometry exploits this fact by using a large computer screen, for example, and it typically displays such kind of stripe patterns with varying spatial frequencies. So typically you display a whole series of images with stripes in horizontal and also in vertical direction. And the first step then is that, of course, the rays of sight of our camera, are reflected according to the law of reflection and will hit some pixel of our computer screen. And now we perform a deflectometric reconstruction, typically that by means of this captured image series, we can solve a correspondence problem so that we get for every camera pixel the corresponding pixel on the screen that our camera is looking at. This allows us to have a triangle here, and then we are able to reconstruct the slope of our specular surface, and we can then feed that into some kind of defect detection, and hopefully we are able to identify as much of those scratches here, for example, on our surface. So found defects would be those green ones, for example, but maybe we might also be missing some of our defects here on the object. And one reason for missing defects in deflectometry is, in our opinion, that those screen patterns that are used here are mainly chosen heuristically. You always see those kinds of patterns. They are robust against defocus. That's why they are typically used. But if you look at such an object as I've drawn it here with a very complex shape, this object itself might have like a mirroring optical function here. So your camera might see some regions of the screen magnified and other regions demagnified, which means that the resolution that you get in your deflectometric inspection varies across your surface profile, which is a thing that we typically do not want. And in order to cope with that problem, we came up with the idea of learning an illumination pattern that is specifically adapted to your actual test object that you want to inspect. Therefore, we need to model the whole thing in a simulation first, and we need to be able to add synthetic material defect to our object so that we can let this whole procedure run iteratively. And in order to generate material defects, we used for our first test the following setup. As a test object, we used a flat mirror with some parabolic valleys in here in order to make it a difficult inspection problem. And then we just added synthetic bumps as material defect on our object. And that is done in the following way. Here we have our mirroring plate, and then we just instantiate a lot of small spheres with different radius and position and then we shoot those spheres on our test object and intersect them with it by means of constructive solid geometry. So we basically add those little bumps to our mirroring plate. And since we do that by purpose, we of course know the exact positions of those defects and hence have a nice ground truth for the following pipeline. So now we are really able to do a complete end-to-end optimization. And in order to come closer to the use case of deflectometry that many people want to see realized, which is one-shot deflectometry, so that additionally we get rid of having to display this series of images and instead can inspect an object by acquiring single image only, so that this whole method gets also capable for being installed inline. And now here we have our example test object. So this is done in simulation at first. We have our screen and our camera. And at the first place, we start with some initial pattern on our screen. This is called the cross fringes pattern. It's used a lot in publications about one-shot deflectometry. And then according to the law of reflection, we will get a first image in our camera. Here you can clearly make out those 4 valley structures. And then we opted to directly feed that camera image into an object detection network that should detect the positions of those material defects here. And now, since we affected the object ourselves by the material defects, we of course now know the ground truth positions of those defects. And then we have the response of our object detection network. We might be able to hit some of those defects, but we also might miss some, or we will have some false positives. That's why we put both of those things into a loss function. And this is the typical goal of machine learning, that you want to minimize this loss function. So you want to get the response of your network closer to your ground truth. But how can we now achieve to optimize the screen pattern? I mean, it's clear that we can optimize the network parameters, but how can we optimize the screen pattern? And regarding this problem, we are nowadays luckily in a very comfortable spot, because this whole simulation pipeline here, there are frameworks that can do this physically realistic and also fully differentiable. And that makes the simulation and the machine learning interconnectable, so that we are then able to calculate the important gradient of our loss function also with respect to our screen pattern fully automatically. And then we can propagate this gradient throughout our whole pipeline. So we can update the network parameters, and we can also update our screen pattern in a direction that optimizes our loss function. So after one iteration of gradient descent, we would then get a new realization of our screen pattern. Then we would choose new positions for our defects that we are not learning them by heart. And then we will get the new corresponding camera image, and we would iterate over the whole process again. Now let's quickly have a look on how the resulting pattern looks. So this was the initial pattern on our screen. And here on the right-hand side, you can see the pattern that results from the optimization. And here you can identify some basically 2 interesting aspects. The first one is that in this region on the downside of our image, there are a lot of pixels left gray, so to say untouched by the optimization. And this is just due to the geometrical orientation of camera, test object, and screen. And this means that all those pixels of our screen have not been observed by the camera at all. So this is a first indication for the engineer to rearrange the screen and camera orientation. And the next thing that we see in those regions that correspond to this parabolic mirror valleys, we also see a lot of pixels that are left untouched by the optimization. And the reason for that is that those parabolic valleys, of course, they have a kind of focal length, and our screen has been positioned in exactly that distance to the object, which means that a lot of camera pixels are all focused only to a tiny spot on our screen. So this would also be an indication that you should modify somehow the distance between screen and object. And now, very interestingly, what is learned by this method regarding our pattern. And when you look at the center of this big parabolic mirror here, you see that especially a very bright and a very dark pixel is learned. And you would observe the same thing when looking at magnifications of those other centers here. And our interpretation of that is that the method learns a kind of dipole structure in our image, which does, when thinking about it in a system theoretical way, this performs the calculation of the first derivative of the slope of our surface completely optically. So the input to the neural network is already the first derivative of our surface, which of course makes it more easy for our machine learning model to detect any material defects. And now we can already get to the third topic I brought you, which is also somehow related to this one, which is about synthetic defect generation. So nowadays, when looking at catalogs of machine learning software suppliers and so on, you might get the feeling that when you want to inspect, for example, such screws with different kinds of material defects, you should follow the approach of just learning everything. So what you would need to do is get a large amount of example defect images of all the kinds of defects that might occur in your application, collect them in a big database, and then use them to train an adequate machine learning model. And if you're lucky, afterwards, this model is able to, when you present it an unseen object that maybe has some kind of material defect, that it is capable of correctly identifying this material defect here. Now, what we have observed with our customers and cooperation partners is that you typically have a very nice catalog of possible material defects. And then when trying to implement something like this, you are asking your partner to provide for every kind of defect, let's say 500 or 1,000 example images. And then there's suddenly a problem, because typically the production process is already kind of running smoothly. So for some of those defects, it's, for example, impossible to produce more than, let's say, 10 examples per week or so. So you would need quite a long time to gather the required amount of data. Now you have two possible ways to get out of this situation by using synthetically generated images that you can use for training. And one way to generate synthetic defects is to use procedurally modeled defects. And this means that if you have a clear physical understanding of how your defects are produced in your process, for example, scratches on a surface or cracks, you can easily, for example, model them by providing coordinates of some points and just interconnecting them with a line. And then in order to create more of those cracks, you can just randomly vary the positions of those points that connect this line, and you can easily generate thousands of cracks. This might also be true, for example, for bubbles or cavities hidden in a transparent material, as we have seen before. You can just instantiate spheres with varying position and diameter that are filled with air, for example, and put them inside your object. And maybe also bumps and dents, as we have seen it in the deflectometry example. You can just shoot spheres or other kinds of geometries onto your objects and either cut out parts of your test object or intersect them and union them with your test object to add these kinds of bumps. So those are pretty solid methods for procedurally generating defects. The problem now is when you do not have a physical explanation of the defects that are occurring in your produced material. And then the next way to get out of this is to use a generative model to simulate more defects. Again, you need to collect some examples of the material defect in which you are interested in, and then you can use them to train so-called text-to-image generation models. I'm sure you have heard of them, like Dolly, for example. Those models you provide with a generation string, like a bear sitting on a bicycle eating a pizza, and then you will get an image of a bear riding a bicycle and eating a pizza out of that model. And there are foundation models that you can fine-tune for your own purpose. But when doing it the standard way, you still need very lots of training data. But however, then you should be capable of using this trained model and then, for example, provide it with a text prompt saying, give me a screw with a scratch, and the model should output another screw with a new scratch for you that you can then use for training your defect detection model. But now you would say, okay, but then again, I need lots of training data. I could directly use that for training my defect detection model. But however, there are very nice techniques that you can use to fine-tune such text-to-image generation models, which is, for example, low-rank adaptation. And they are capable of fine-tuning the weights of those models by only using very few example images. And we have worked on that example for one of our partners. They are producing those components that you typically find at the ceiling inside a car that allow you to control the lighting conditions and so on. And they had to cope with a defect they called Schlieren, which looked like those white smear-like particles that could occur on the opaque parts, but also on transparent parts, as you might be able to see here on their test object. And they were not able to figure out the physical cause for that kind of defect. And so we really tried to solve that with a generative model. And in the end, we were successful by only using those 5 example images that you see above here, only 5, to fine-tune a foundation model by using a low-rank approximation technique. And this then allowed us in the synthesization step down here to create really hundreds of novel instances of Schlieren defects, examples you can see down here, that we could use for training a defect detection model. And if you try to compare them, I would suggest that you are not able to identify which of those are generated and which were the training images. And now this brings us to the final topic that I got for you today, which might be the most unconventional one, which is deep signal-to-noise ratio estimation for Wiener filtering in lensless imaging. Now, the optimization for that, for lensless imaging, might be the following use case. Again, it might be your goal to inspect screws for some kind of material defects. And what you typically do is you select the corresponding lens system, the corresponding objective lens, to get a clear and sharp image of your screw on your sensor, and then you continue with all the development of the image processing. Now, unfortunately, in reality, the objective lens is not, as I've drawn it here, a single lens that you put somewhere in your system, but it's typically, especially if you think about telecentric lenses, those are really huge objects consisting of a lot of optical components, what makes them, of course, kind of expensive. And they are typically also very heavy and bulky and require a lot of space in your application. And especially if you want to integrate a vision solution in an existing process with limited space, this could really be a problem. And so maybe in the first place, very naive idea would be, okay, then let's just get rid of our lens and use something else. And then you might think about, okay, what is this lens supposed to do? What material is it of? And of course, it is transparent and has some kind of optical function. Then you might look around your desk looking for something that is also transparent. And maybe you might see a piece of teaser tape, which is, of course, also something transparent. And also interestingly, if you look at it microscopically, it shows this kind of smooth but randomly varying surface profile. And this makes it a perfect optical diffuser. So it is transparent and has some kind of optical function. But now, if you insert that into your optical system, you will make the following observation. The image that you get from your screw will look something blurry like this. And I think your image processing engineers will not be happy if they were supposed to extract any material defects out of this blurry image. Already disappointed, you might start experimenting a bit with your setup, and maybe you would move your screw a bit upwards, and then you would observe that the pattern shifts on your sensor, just according to the shift of your screw. And this might remind you of your early lectures in system theory, that the image formation process that you have here might be expressible as a linear shift invariant system. And exactly that is the case. So the image G on your sensor can be expressed as a convolution of the intensities of your screw in which you're interested in with the point spread function of your optical modulator. And you can easily acquire this point spread function just by presenting a point light source to this optical modulator and then recording the corresponding image that you get on your sensor. But still, you might ask yourself, how is it now possible to extract this S in which we're interested in from this blurred observation on our sensor? And maybe then you might go further back in your in the things you remember from your first image processing lectures, and you might recognize that there was this thing called Wiener filter that allows to do exactly that, extracting a hidden signal out of a blurred observation, which is generated by a convolution of the signal with some kind of point spread function. And the Wiener filter comes to its solution by looking at the problem not in the spatial domain, but in the Fourier space, where it is very convenient that this convolution is turned into a multiplication now, which is much more easy to handle. And luckily for us, Norbert Wiener came up with his great filtering idea somewhere in the last century, which he could show that it is the theoretically optimal solution for obtaining this S out of a blurred observation. The formula looks like this. We won't go into details, but we can have a look at what we need. We need the Fourier transform of our observation, no problem. We need the Fourier transform of the point spread function. That is also no problem. But then this tiny term down here is really problematic. This is the so-called signal to noise ratio, which is a very crucial component of the Wiener filter. It basically tells us, or should tell us, for every spatial frequency, whether our signal has the most energy in our observation for that spatial frequency, or whether it is the noise. And if we have a low signal to noise ratio, then we should better not try to reconstruct the image at that spatial frequency, because that will enhance any noise that is present in our observation. So although this Wiener filter is theoretical optimal, its practical applicability is largely hindered nowadays because we don't know the true signal to noise ratio. We can only try to estimate it. And here we came up with the idea of now exactly for this point using a machine learning model for learning this signal to noise ratio. So the idea is to use a model that is able to solve a pixel to pixel regression task and to train it by using our blurry observations as the input and the ground truth SNRs that we are of course able to generate if we ourselves generate the corrupted images as the expected output, and to use such pairs of images to train this network. Now this is what looks a bit like an astronomic nebula thing. this is actually the signal to noise ratio. It looks like this because it's something that is located in the Fourier space. And now we can actually use such kind of image pairs. Here's another one to train this kind of image-to-image neural network. A prominent architecture would, for example, be a UNet that you can use for this task. And now if we have a new observation that is heavily blurred, we are able to feed it into our trained neural network. Our network will respond with an estimation of the signal-to-noise ratio. Then we can, as the next step, set up our Wiener filter, where we have Fourier transform of our observation, the Fourier transform of the point spread function that we have estimated before. And down here, we have the signal to noise ratio. And now we can insert this output from our network for the signal to noise ratio, compute the Wiener filter, do an inverse Fourier transform, and then we will get a crispy, clear reconstruction of our blurred observation. And we did some further experiments with that technique. Now the following results that I show you are not for a lensless system, but for observations that are affected by motion blur. That's just because this is the common database for evaluating such deconvolution algorithms. And if you look at the result that we can obtain here, you suddenly get a clear image of this shaky and blurry input. And also a second example here of this blurry church image. And also here we were able to create a very clear reconstruction. And besides this interesting technique, maybe the key takeaway here I would like you to take home is, which was also very interesting for us, that it's sometimes a good idea to step back a bit from all those trends of trying to learn everything and have a look also at the history. For example, the Wiener filter is theoretically optimal, and to use such a thing and only replace that little component inside there that is actually hindering its practical applicability. And therefore, of course, as we have seen here, machine learning approaches are a very viable and valid solution. And that finishes the topics I brought for you today. I hope it has been some kind of unconventional for you. And if you have been inspired and have some idea for projects, for elaborations or whatever, please feel free also to contact us.
So thank you, Johannes, for the great keynote. And I'm looking for the question. And I think the first question is about the deflectometry technology. How does the method cope with varying positioning of the objects?
Yeah, so I quickly go back to the corresponding slide. This was this one. And here we had the optimization thing. So I guess the question is, since now this pattern is optimized for our object in some kind of location, and how does whether the method is robust to misalignments of this object later in the practical application. And that's indeed an interesting point. We did not really evaluate that yet, but you can easily try to cope for that during the learning procedure by also varying the object position a bit from every iteration to the next iteration. So that will make it kind of robust, but of course you should try to make sure that to the extents that are mechanically possible to have it in the same location.
Mm-hmm. And then there's a question to Wiener filtering. Which kind of machine learning neural network algorithms are used for the estimation of SNR in the application of Wiener filtering?
So this might be related to this slide. Which kind of neural network we are using here for estimating the signal to noise ratio. And basically you can use anything that is capable of doing a pixel to pixel task, because as the input for our network, we have image-like structures, and the output are also image-like structures, so not a label or something. And then the architecture that you use should be capable of doing that. And as I said, for example, the very prominent UNet architecture, which is also kind of illustrated here by those blocks, is a valid choice.
Now I have a question by myself. Are there other applications besides lensless imaging for which one could employ that deep SNR-based Wiener filtering?
Yeah, so basically the range of possible applications is quite broad. You can basically use it everywhere where you have to solve a deconvolution problem. So as already illustrated here, when you have observations that are blurred due to motion blur, for example, you can use it. Or if you want to extend the depth of field of an existing optical system, you can also try to use it, because as soon as you move out of your focal plane, the optical effect you get is also a convolution with a kind of point spread function that you could try to invert using this approach.
Question about synthetic data generation. What model is used for synthetic data generation? If it is a closed source model, is there an equivalent open source model?
So I guess, sorry, this was this slide, I think. Here, this one, which model we used for the generative defect generation. For our first test, we used a publicly available model by I think Hugging Face is the name of those guys, and it has been the Dream Booth model. So this is publicly available, and you can use that. I don't know about the license requirements now out of the blue, but I think that should be solvable.
I think we have time for a last question, and it's about the inverse light field illumination. What can you say about the maximum possible size of the test objects?
This was this slide here, and here we had the image about how this procedure works. And I think the question is about the maximum possible size of those objects here. So we have to speak about two different dimensions. The first one is the lateral dimension with respect to the optical axis. Of course, there you are limited by the diameter basically of your telecentric camera system that you are using here. Although colleagues of mine are already experimenting transforming the idea by using endocentric camera, so then this field of view problem would be solved. But nowadays that would be a limitation. And then of course in axial direction, you have the depth of field of your camera that is limiting the size of the object.
So Johannes, once again, thank you very much for your presentation.